So in this video, I'm going to begin to describe motion mathematically and a few ideas, basic ideas in motion. So let's say in the summer I wanted to take a trip to Seattle from Asheville. So I start over here near Asheville, and I have different routes that I could take. So let's say I just decided to go this way through Texas and up through California into Seattle that way. Okay. Or if I wanted, I could drive up into the East Coast, do some traveling, then come back across the country and end up in Seattle over that way. Or maybe I wanted to go up and visit my family in Wisconsin and Minnesota, and then go through North Dakota, Montana, and end up over that way. So in each one of these instances, I went from Asheville to Seattle, but I traveled a different distance. Okay, so distance is actually the amount of ground that you've covered. So the amount right? So this one may have been like, and I'm just guessing here, maybe this one was like 2,000 miles and this one was 2,500 miles, and maybe this one was like 1,300 miles. So each one of those different paths that I took was a different distance. Now, as I moved along, I went different directions. There's no one specific direction. Distance only has a magnitude, so it is a scalar. Okay? Now, if I were to travel, let's say, if I could drive straight from Asheville to Seattle, okay, in a straight line, let's just connect the dots. For each one of my trips, my change from my original position, which is here, to my final position here would be exactly the same. Right? So even though this trip was more miles than this trip was, the difference from where I started to where I ended up is exactly the same. It's this straight line. That line right there is called your displacement. So that is displacement. And displacement is your change in position. And so for this case, let's just say, and I looked it up so I know, my change in position from Asheville to Seattle is actually 2,892 miles, 25 degrees north of west. All right? So this here, because it has both a magnitude, the number of miles, and a direction, displacement is a vector. So just keep that in mind, the difference between the two things. You have your distance, which is a scalar, which is the total number of feet, meters, miles, whatever you have covered. And displacement is your change from your original position. And it's a vector because it has a direction. Now, if we wanted to calculate this, how you indicate change in position, in mathematics, if we're going to put change, we use a delta symbol. So that would be change, and we use x. That's what's used in your reference table. However, I most likely will use a different variable because this x implies that you're moving horizontally, which you're not necessarily always moving horizontally. You might be in a vertical plane, so we might have a y coordinate. So, x is generally used, but I'll probably start to use d so we don't have to worry about, what direction you're actually going. So the change in x, or your change in position, is wherever you started, so your original position, wherever you ended up, so your final position, minus your initial position. That is your change in x. Right, and I'll bring that up here in just a second when we add some time into it. Okay, so if you look at this map, right, every single way that I traveled took a different amount of time. Time passes. So we want to relate the distance that we've moved or the displacement that has occurred to time. And when we do this, this is what speed and velocity are. So I'm going to start with instantaneous speed. So instantaneous speed is the speed that you're going right now, like if you were to measure with a radar gun. So instantaneous speed. And that's measured by the distance that you cover in a certain time interval. Okay? So speed equals distance over time. Because distance and time are both scalars, speed is also a scalar. And in physics, we need to have units with every single number that we represent because that tells us what that number means. So whatever you do to the numbers, you also do to the units. So if you take a distance measurement, so distance in physics we use meters, and then you divide that by a time measurement, so it'd be meters per second. Okay? Now instantaneous speed, like I said, is the speed that we would measure with a radar gun. However, you know if you're traveling on a long trip, you're going to stop, your speed's going to go up, it's going to go down. So there's also average speed. Okay? And this isn't taking the averages of all the speeds that you went the entire time. What it is you take the total distance you traveled divided by the total time it took you to travel that distance. And that will give you average speed. Right? So let's then compare this to velocity. So speed is a scalar, it's distance over time. So if we look at velocity is very similar. Those two terms sort of, seem the same to us, okay? But there is a difference in physics. So velocity is a vector, okay? And the reason why is because the definition of velocity is your change in position over time, which, remember, if we look back here, remember that change in position is displacement. So velocity is displacement over time. So the unit is also meters per second, okay? However, when you express a velocity, because it's a vector, you are going to not only say a unit, but you are going to include the direction. The distinction between instantaneous speed and average speed also applies to velocity. So you can have instantaneous velocity or you can have average velocity. And average velocity would just be the total displacement over the total time. Alright, so let's say we're observing a car moving, right, at a constant rate. Let's sort of graph what is happening over time. So this is x and this is t. So this is your position and this is your time. And we'll just give some units. So let's say 10 meters, 20 meters, 30 meters. So let's see, you look at the car and after 1 second, the car has moved 10 meters. Okay? After 2 seconds, the car has now at a position of 20 meters. And after 3 seconds, now the car is at a position of 30 meters. Okay, so let's connect the dots. That's a linear graph here. Right. Now, if I wanted to calculate the slope of this line, remember that slope is rise over run. So according to our graph, that would be change in position over the change in time. What is that the graph for, or what is that the equation for? That is velocity, right? So the slope of a position versus time graph gives you velocity. So the slope of position versus time graph is velocity. Alright, so let me just give you an example of a, another just basic graph, right? So we know that this is some positive constant velocity. It's not changing. There's one slope, right? Let's look at one where, let's say we look at the car and the car's just sitting still, right? If the car's sitting still, then its velocity should be 0. So this would be the slope of a position versus time graph for something that's not moving. So this is at rest, right? Now let's say something's going backwards. That would be starting at some positive x and moving back this way. So we'd see backwards, we would have a negative slope, right? And then we'll take it just one step further, and I'll go more into detail about this a little bit later. Let's say something's not going at constant velocity. Let's say it's speeding up or slowing down, okay? So if you're speeding up, it means that your slope would increase over time. So your position versus time graph would look like this. So it's somewhat of a parabola. It's quadratic. And that's just to introduce to you what we're going to talk about in the next video, which is acceleration.